Welcome student to the next lecture, that is lecture number 11 of halogen derivatives, and we are continuing SN2 mechanism, and today we'll study what is the factors affecting SN2 mechanism. Okay, now the first and the most important factor is hindrance. What is that? Hindrance. Now, when I say hindrance, what does it mean? It means that suppose I take one example. I have CH3Cl, right? And next I have CH3 3Cl. This is 1 degree and this is 3 degree, right? 3 degree alkyl halide. Suppose I have a same nucleophile, that is OH minus. I have same solvent, right? Everything is same. And now if I say SN2 mechanism will be taken in the better way, in which this is, suppose this is A and this is B. So the reaction will take place easily in A than in comparison to B. Why? Because here the hindrance is more. When I say hindrance, what does it mean? Let's see. And actually hindrance decides SN1 or SN2 mechanism. But since we are talking about the factors, I'm telling you. See, carbon is there, hydrogen is there, hydrogen. When OH minus attacks, it has to come to close. And this can come to the close because this hydrogen is not stopping this OH, right? But if I have this carbon, right, suppose here carbon is there, here chlorine is there, instead of hydrogen I have methyl group. So when I said methyl group, this will also have hydrogen like this. Here also there will be hydrogen, right? So there is very much crowding. OH minus cannot come close to the antibonding orbital of this carbon. Okay, so it is not going to, it's not able to put its electron in the orbital of this carbon. As a result, this reaction is not going to take place. So this point is the most important point, student. Hindrance, right? So if hindrance is less, SN2 mechanism reaction will take place easily, right? Second factor is nucleophilicity. What is this nucleophilicity? Right. See, this nucleophile which go and attack, right? Suppose a powerful nucleophile is there. Right, a powerful nucleophile, so it will go fast and it will put its electron very hard. Okay, and after putting its electron, right, the leaving of electron will also take place. It will be faster. Okay, so we call them as a hard nucleophile. Right, there's the hard nucleophile, there's a soft nucleophile, and there's a moderate nucleophile, right? If there's a hard nucleophile, reaction will take place faster. Okay, student. Okay, so which is hard nucleophile? Understand? If I have H minus, if I have CH3 minus, or that instead I say R minus. Okay, they're all hard nucleophile. Now, let's understand why they are hard nucleophile. First example, let's see example also. And then I'll explain how. Suppose I have RO minus, I have NH2 minus, they are moderate. If I have Cl minus, if I have Br minus or I minus, they are soft nucleophile. Okay, now we have to understand why that happens, why they are hard, why they are soft. Okay, now student, When I say electronic wave is present in hydrogen. Now, hydrogen is very small atom, student. Hydrogen is the smallest of all atoms. This small, little, tiny hydrogen is not able to hold two electrons, which he got from other. I mean, one electron of his own, and somebody has put one electron in his orbital. Right, such a small hydrogen orbital is not able to withstand or hold this electron. So he wants that this electron should be given to someone else, right? And he is in very hurry because he can't hold that electron, right? Assume you're holding something which is very, very heavy, right? And you are not able to hold it. So what you want? You want that somebody should take that so that you become free, right? Okay, so this is very small, this is very tiny. Same way methyl. See, when I say carbon is less electronegative. When I say it is less electronegative, that means to hold that electron, right, the capacity to hold electron is very, very less. So he can't hold that electron. He wants to get rid of that electron. He wants to give that electron to someone else. Similarly, R group, when I say, they are a hard nucleophile because they don't want to hold the electron. They want to get rid of that electron. They want to put those electrons into someone else's orbital, right? So that's the reason they are hard. Now, why they are soft? When I say oxygen and nitrogen, understand, student, oxygen and nitrogen, they are more electronegative. Oxygen is the second most electronegative element after fluorine, and the nitrogen is the third most electronegative element, right? So they can hold the electron, right? Since they can hold the electron, okay, they are not in that much hurry to remove that electron. That's why they are moderate. When I say they are soft, why they are soft? Because, see, you will say, so they are comparatively less electronegative. But when I say chlorine, bromine, and iodine, student, chlorine, bromine, and iodine have large orbital size, whereas oxygen, being second group element, okay, their orbitals is small. So if they have large orbital, the electron can reside more easily. So the tendency to get rid of this is less. That's the reason chlorine and bromine and iodine likes to take the electron, because they make them stable. Because they see, the need or the requirement of electron is also greater for oxygen and nitrogen, but they don't have space, right? So if they take the electron, that electron will satisfy that thought, but actually they don't have that space. So that is going to create problem for them. That's why the tendency to keep that electron, although they want, but they can't. The reason, size is less. Okay, so these are soft nucleophile, these are moderate, and these are hard nucleophiles, student. Okay, so when I say when you have to solve the question, you have to keep all these things in mind, because that is what is going to make you help to solve the question. That was second. Third one is nature of Lg. Lg. What is Lg? Lg? LG is not your television, student. We are not talking about the brand LG. Here LG is what? LG is living group, right? What is this LG? LG is living group. Okay, now suppose I ask you, I have chlorine, I have Br minus, I have iodine minus, right? And same nucleophile is there, we're going to attack them. Can you tell me why the reaction will take faster? Obviously iodine, because this is the sizes are highest, orbital sizes are highest of iodine comparison to this. So chlorine, here the reaction will take place slower in comparison to bromine, in comparison to iodine, right, student? Okay, now moving to the next factor. is solvent. Remember, I've told you in last lecture that solvent also plays one role, because this OH minus, which was attacking the carbon, right? They are present certain medium. Okay, so solvent plays a major role in this. Now, when I talk about SN2 mechanism, okay, here non-polar solvent helps to increase the rate of reaction. Why? Let's understand. See, when I say alkyl halide, that is Rx, then this R is partially positive and this is partially negative. Suppose I take some polar solvent like water. So when I say water, the water is like this, right, student? Oxygen is partially negative, hydrogen is partially positive. So here the positive and negative will have some force of attraction. So if this have some force of attraction, then it's very difficult to go and attack. Same way when I say OH minus, so that means OH minus, that nucleophile will have some attraction with what? This R. So the OH minus, which is present in hell amount of liquid. Okay, so suppose this whole liquid is present, OH minus is present, and this water is trying to stop that OH minus. So when this OH minus is not able to move, so the movement of OH minus, that migration of OH minus, CH3Cl, suppose this OH minus is present and this OH minus is surrounded by hell amount of water. So this movement of OH minus to come and attack on this orbital, anti-bonding orbital of carbon, it will be very, very slow, because this water is not allowing this OH minus to move, right? So that's why the solvent also plays one major role, a very important role in the mechanism of a reaction, in the rate of reaction, student. So which solvent is going to support this SN2 mechanism? So answer is polar, non-polar solvent, because if polar solvent is there, then OH minus will be attracted by them. So non-polar solvent is going to help this reaction mechanism. Clear? I hope this point is clear, student. Now, once you understood this, we can solve few problems based on that. Okay, let's solve the first one. Now question is, suppose I have CH3Cl. This is first A, B is CH3, CH2Cl, C option CH3, CH, CH3Cl, and D option CH3, CH3, CH3Cl. Tell me, or arrange this in the increasing or decreasing order of reactivity. Okay, so how to deal with that? Now understand, student. In all the case, leaving group is same, that is chloride. That means here this reaction will not depends upon leaving group. Seeing the four factors, right? So this is not going to depend on leaving group. So solvent, now I say suppose solvent is also same, so it is also going to depends upon solvent. Okay, so leaving group is same, solvent is same, right? One factor was hindrance, student. If you remember, one factor was hindrance. And when I talk about nucleophilicity, suppose I take in all the case OH minus, so the nucleophile is also same. So three factors same. In all the case we are using same nucleophile, that is OH minus. In all the case I'm using the same solvent, some non-polar solvent, so that is also same. In all the case, what is same? Leaving group is same. So only one factor is left, hindrance. Now it's very simple. Where the hindrance is less? Obviously the hindrance is less in this, because carbon is attached by 3 hydrogen. Here carbon is attached by 2 hydrogen but 1 methyl group is there, so that will hinder, crowdedness will be greater, right? How you understood this? Suppose C, I have H, I have here H, here I have CH3, so this H, and this H, so it creates crowding, right? In this case, carbon is attached to 1 and 2 methyl group, so here the crowding is further more, and here the crowding is highest. So the rate of reaction will be highest in A, then will come B, then will come C, and then D. So you have this option, then this option is going to be correct. Okay, now moving to the next question, student. Now let's see the next question. Second question is, suppose I take CH3F, CH3Cl, CH3Br, CH3I. Suppose this is A, this is B, this is C, this is D. Now student, here in all the case hindrance is going to be seen, right? I assume solvent are also same, I assume nucleophile is also the same. So it depends upon what? A living group, right? It depends upon living group. Now tell me, in this case where the rate of reaction will be highest. See, actually if it's fluorine, chlorine, bromine, iodine, electronegativity of fluorine is the highest, but when we talk about size, the size of iodine is highest, and when the both factor is present, right, that is size as well as electronegativity, then size dominates over electronegativity. Okay, you yourself understand, student. Okay, now here it will become F minus after living. Here it will become Cl minus, here it will become Br minus, here it will become I minus. Which is going to be more stable? Iodine is going to be more stable. Reason? Because it has to have big size. Size is big, orbital size is big, so electron can easily be accommodated in that. When I say fluorine, although the electronegativity is more, right, again I'm saying here the tendency to take the electron is more, but space is less, right? So if electron comes also, they will not be stable, right? But here in this case, here electronegativity is comparatively less, but the space present is more, so the electron residing here will be more stable. Since this is more stable, so the tendency of reaction will also become faster because the byproduct which is formed is stable, so it will have tendency to take the electron and move away, right? So I can say D is greater than C, then B, then A. I hope you understood this, right? We'll take one more example. Suppose CH3, CH, CH3, CH3. I have this, I take here Cl, not CH3 but Cl, right? Okay. I react this with different reagent. Suppose first reagent is A, I call CH3 minus. Second is going to be NH2 minus, this is B. Third is going to be OH minus, this is C. The fourth one is going to be F minus, this is D. Now student, carbon, nitrogen, oxygen, fluorine. carbon, nitrogen, oxygen, fluorine, they are present in the same period. They are present in the same period. Okay, since they are present in the same period, that means the size is almost same, right? We do understand that when we talk in group, then the size matters, but when we talk in a same period, here electronegativity plays a major role, right? So we do understand the electronegative fluorine is the highest and the carbon is least. Okay, so the tendency to take, suppose I attack this with CH3 minus. Now this CH3 minus is more unstable. It have very least tendency to hold that electron. He wants to get rid that of electron. So the reaction will be faster in the case of CH3. You're getting? So here A, then comes B, because electronegativity of nitrogen is less, here this is least electronegative, then comes nitrogen, then comes oxygen, then comes fluorine. Fluorine is the highest electronegativity. Okay, so A, then B, then C, then D. I hope you understood this, student. Why this will do the reaction faster? Obviously because the tendency don't want to hold that electron. He wants to get rid that of electron. He wants to lose that electron. But in comparison to NH2, here electron is less stable, so he wants to get it rid of it faster. In comparison to OH, nitrogen has less electronegativity. In comparison to fluorine, OH has less electronegativity. So the order will be like this. Right? This is on the basis of electronegativity, whereas this was above question was on the basis of what? Size. Okay. We'll do one more question, student. CH3, CH3, chlorobenzene. No, we take this is what? Tell me the name of these. This is chlorobenzene. This is hexacyclochlorone. Okay. Now, tell me now, where suppose I call this A, I call this as B, I call this C. Okay. Tell me where the reaction will be faster. Think and tell me, student. It's a very important one. Now, actually the reaction will be faster over here. A will have a higher rate of reaction in comparison to B, in comparison to C. The reason is it have hindrance of CH3 and CH3. Okay, but then also the OH minus can come and it will have a small tiny path by which it can move over and can give this electron into anti-bonding orbital of this carbon. But here actually it's in a ring, cyclohexane, right? It has a ring. So a chlorocyclohexane has a ring. It's I'm talking about this carbon. Here will be anti-bonding orbital. So it is surrounded by all the side. So it have to come and give its electron from either from the up or the below the ring, right? Okay. Here in this case, when I say it's a benzene, that means actually they are bonded, right? So if you remember here, there are the lobes which is going up and down, and in these lobes electrons are present. That means this OH minus can't attack from upside, also can't attack from backside because the lobes are present above and below the plane also, and can't attack from here because this is in a circular ring. So to put that electron OH minus in the orbital of this is very, 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 very difficult, student, right? Up to impossible, right? So that's here there's a slight possibility. Here obviously there's some possibilities, right? So if I talk about the reactivity is going to be like this. A will be highest, then comes B, then comes C, right? Okay. Now, One thing more, student, if we talk about stereoisomerism of this SN2 mechanism, when I say stereoisomerism, what does it mean? Let's understand. Suppose I say C, here I have R1, here I have R2, here I have R3, and here I have Cl. Right, but this R1, R2 and R3 are different groups. They're maybe not necessary it is alkyl group. Okay, for example, this is R1 hydrogen, this is some CH3, this is some C2H5, and this is chlorine. That means this carbon is asymmetric carbon. I hope you're getting. Right, R1 I say hydrogen, R2 I say methyl group, and this R3 this is suppose ethyl, and this fourth group is chlorine. So totally four different group is present. That means this carbon is asymmetric carbon. Right, now when this OH minus will come and attract, okay, so this and one thing understand, student, suppose I say I draw it like this is in plane, this is in plane, right? This is going away from us and this is coming toward us. If you remember, we have understood that. Okay, so this is a plane, this is moving away from the plane, this is coming towards me. Okay, now when this OH minus will attack, understand that when it is going to form a bond, actually it becomes pentavalent. Are you getting that? For time being, because here the bond is forming and here the bond is slowly breaking. So time comes, the stereochemistry of this changes. Okay, what happens? This carbon, suppose this R1, okay, here I say R2, here I say R3. Now they comes in one plane, right? In one plane, and assume it like this. Suppose carbon is present, this is R1, this is R2, and this is R3. So one bond is forming from here and one bond is leaving from here. So I'm saying this OH minus is coming. Suppose this is coming from back side. So from front side, this Cl minus is going to move out. So time comes when it become pentavalent, slightly pentavalent, and this become highly unstable. Right? This become what? Highly unstable. So stereochemistry is this. Okay, these three are in a one plane, and this is out of plane, and this is also out of plane. Okay, so now when this OH comes in, okay, initially it was assumed like this. It's when you know what is tetrahedral structure, student, I show it. Suppose this is what it's like this tetrahedral. When I say these three is like what, and it's here. So when the electrons, when this OH minus come from here, okay, they come in plane, they come in like this plane, and when it form a bond, this changes. Okay, it's like this. You know, you see umbrella. Okay, so sometime when the very high amount of breeze comes, okay, so umbrella get turns, right? In the same way, initially it was like this, but when OH forms a bond and Cl leaves away, the stereochemistry changes. Okay, so C, here comes OH, and this become like this. Suppose R1, this is R2, and this is R3. Okay, right? If assume it like this, Cl moves out of from here and OH comes over here. Means from where the bond is broken, at the same place the bond is formed, I call this as a retention. But here is SN2 mechanism, the retention does not take place. Then what takes place is called inversion, and we say there's an inversion in configuration. What is that called? Inversion in configuration. Okay, student, understood that? Okay, this is a condition where there is a hell lots of instability, right? Okay, and there's something called as energy profile diagram. Okay, but it's not possible to show it now. Obviously we will be doing that in next lecture, and after doing energy profile diagram, then we'll start with SN1 mechanism. Okay, almost SN2 mechanism is completed. So one energy profile diagram is there, otherwise this is completed. Okay, so we have studied this SN2 in great depth with examples also. Study well, because this is the most important part of the chapter. Okay, thanks for watching, student.